Okay, so text clustering. So we had some examples from yesterday already, so let's move on. Query relaxation, this is typical for Google search. Also in Opsi we have the same, except we don't do any clustering here. We should. So what we have is a very simple storing of the previously used keywords. So we have a database what people have typed in. But you can see that it will be operated by kahvela, kahvi or kavela. So all typing errors and different variations are there. So maybe we should just propose the user kahvela or some cluster them together and propose the representative. And also typing errors. So if you write in Google, you know that it's already correct. They give you the make the search based on the correct word and not the misspelling. So okay. One example, so spell checking. And then categorization. We want to present users set of possible services that are available. For example, this can be found in Mopsy. And if we want to give menu that doesn't contain 100 different items, but just 5 where to jump in, so we need to cluster it again. And then this is an example how they are clustered in Mopsy. And what the data we use, it's not necessarily just the text here, what we are talk about. So in that sense, it's more than just text clustering. So we may have using the other information of the service like keywords and whatever. So this is just an example what kind of the applications there could be. And also documents. So document can be Word files, Excel files, text, and whatever, usually textual information, but also almost anything. Okay, now if we consider the content of a text document, for example this page here, so it's basically one big string. Okay, we ignore the image here, just take the text content. It's just a few words, but if you take the entire document, it may be much bigger. So the key problem becomes how we calculate the similarity. As long as we can define the similarity, then we can, after that, apply clustering. Okay. There are two types of similarities, semantic and syntactic. Okay, semantic similarity like car and auto, you can have a different version of the word meaning the same thing. And also yeah, okay, syntactic similarity means that the form how we rephrase the same. I just realized that I have old slides here. I forget to copy my new ones here. Okay, so what do we do with the semantic similarity? If we don't have, so how we know that car and auto is the same or apple and oranges are more similar than apple and bicycle. So we have to have some context about this. So one typical resource what is used is WordNet, and WordNet is a stored hierarchical structure of all possible, well, not all possible, but as extensive amount of English words as possible, organized so that there's a very general words at the beginning, like object, and then object is divided to subcategories. Artifact is one of them, further divided and so on. And the deeper you go, this object, you can come to transport, after that subcategory vehicle, wheeled vehicle, so boats are somewhere else. This is automotive motor, bike, bicycle, and so on. So you go the deeper in the tree we go, the more specific the item comes. So now we assume whatever word you have, it's somewhere in the tree. It's actually quite big tree. And then if we want to measure the similarity of two objects, let's suppose like we want to measure similarity of fork and bicycle. Okay, so they are not completely dissimilar. They are something similar. They are objects. As you can see, they belong to the same subtree. But how far, how much similar they are? So this what the word net is indirectly used. So the location in the tree structure is how it's used, how to measure. Okay, another example of part of the word net somewhere. There's a group category animal divided to mammals, and then wolf is one subcategory there. Dog is another one. If we go further in the dog, we will get hunting dog. And now let's say supposed to have what's the similar to wolf and hunting dog. Yeah, probably if you are not a Finn or you don't live in the Eastern Finland, you might know that people are actually afraid of wolves. And not because they are coming to eat you, they might come and eat your pet, or even the little babies. They don't really do it, but people are really scared that they at least some people. And then the other people want to protect the wolves. So this is very emotional. So anyway, and then there's a hunting dog. Okay, this is a good fellow, and this is the bad guy. So they must be very dissimilar. But yeah, they are quite similar. At least according to WordNet, you will find out that they are not so far from each other from the tree. So now what we need to define is the distance. Okay, we could principle just calculate going to the farther and farther nodes as long as we come to the same how do you say grand parent, and then go back down to the other object. So this length of this path could be used, but now for some reason this Cohen-Palmer's measure become quite popular, but it's just a little bit different variation. So what it basically does is to calculate the distance from this level where this hunting dog or this one object is to the common great grandparent, and then the distance from there to the other one. So these two distances, depth and depth. Okay, not this distance because the distance from here to root, this is the depth what this measures, and the distance from here to the other one depth is what it measures. But then it also calculates the depth from the common grandparent. So if the common grandparent is at that level, then this distance is kind of subtracted away. So the actual equation is a little bit more complex like that, but basically calculating this distance, we could calculate the distance from here to the root, from root to here, and then subtract the distance from root. And if you do it twice, then if you think about it carefully, yeah, it actually does it. But instead of subtracting, it takes the ratio of the difference of what is the twice from the grandparent to the root, so what is this distance, and then sum it this plus that. So it gives kind of what is the difference, this one. So if you really analyze this equation, you will find out that these two differences, their sum relative to this distance here. 2 is just because you are here 2 objects and so on. So, okay, so intuitively it should be clear what is the idea of here. And it's just an approximation. So as a result of this, it will give 0.85. So the distance, hunting dog is at level 14, wolf is at level 13. So if you put here, so the grandparent is level 12. So 2 times 12 is 24, divided by 13, and 14 is 27. So it's 0.89. So almost the same. Okay, so that's one way. If you want to have this kind of semantic similarity, having WordNet, yes, we can do it. And then now problem comes in practice then that now this is only for English language. And if we have some other language, we should have it available. And we would end up to have huge amount of different libraries. And then, okay, Gregory.
Where do those numbers 12, 13, and 14 come out? Where did they come from?
This animal is at level 11 of the tree, so this is a subtree. So this entire tree continues higher. So this animal is at level 11, mammal is at level 12, and walking 13. Dog is at the 30 and hunting dog 14.
Right.
So it comes from the WordNet and only part of it is shown here.
Okay. Thank you.
Yeah. So the second problem is that we should know the language. Okay, if you have good tool to detect the language, then no problem. Let's detect the language first and then use that dictionary there. Fine. Google does it all the time. It even have automatic translation. So in a sense, it's understandable this could be used, but for your everyday application, it's a little bit heavy tool. Okay, now I think this was from somebody's master thesis. So using this WordNet now, using that similarity, we can use hierarchical clustering. So now the agglomerative clustering I didn't teach you yet, but similarly, if you remember, I might mention that this is one example of them. How we define the difference, and complete link was another example. So here have we studied just 5 objects: car, orange, bike, bus, apple, clustering 10. And this algorithm is this kind of merge based. So at every step, so it starts putting everything into own cluster. So actually start from here and moving up, merging the two that are closest. So it basically measures all possible similarities, and the most similar it finds is car and bus. Okay, numbers are not shown here, but huge computer scientist nerds always process the milliseconds. So car and bus go to the same cluster, and then next level you measure. Now, then of course you have to think about it, how we measure car and bus and orange. How is the similarity? Because in WordNet you don't have it anymore. Car and bus is not there. Car is there and bus is there, but so what do you think? How to measure similarity of these two? Okay, no answer, so it's a good exercise task.
But why orange is not in WordNet?
Orange is there, but is there such a car bus? What? Yeah, we could concatenate, but I don't think there's a car bus in WordNet. So in order to make the next pair to be merged, we have to calculate, okay, orange and bike and apple, we already know the similarity from the WordNet. But what is the similarity of car bus cluster and orange cluster?
You take the subsummary of them both.
Okay. So yeah, let's assume we do it some way. Now you have to think of it your own. And then somehow it finds out that when car, bus, cluster and bike, their similarity is best or most similar. So they are put in the same cluster. So that happens. So next level. Then it finds out, only after that it finds out that orange and apple are more similar than these cars and buses. So they are merged. So at this level we have these two clusters, and finally there's nothing more to do, they will merge them. Yeah, here you can see also that the number of clusters, of course, has to be decided somehow. If you know that there are two clusters, then we stop here. And this is our answer. Nice. Using WordNet, we can use quite easy clustering of this kind of. And yes, of course, how we measure the similarity exactly, and how we minimize or what we minimize or maximize, then this complete link and single link are a little bit different strategies, but we will come back later. Okay, so it was just one example of how we can do clustering. Now, let's suppose we don't have WordNet. We have some exotic language, so we don't have enough resources to buy or purchase these dictionaries. So we have some cryptic language only given. It's a fuzzy speech language. It's almost like English, but not exactly. There isn't WordNet yet for Finnish. So that's why it's quite attractive to think about syntactic similarity. Let's just consider whatever the text is there. So I focus a little bit now on this. So operate on the words and their characters, no, language independent, no tools needed, no extra dictionary. So how we measure? Now we have apple and appelsini. orange. Yeah, the bad examples in the sense that here you need the language, or actually language translation to conclude that appelsiinen orange is actually the same fruit. The Finnish orange, surprisingly. So it's not actually apple. Finnish apple is pomelo. Okay, but consider that you search for the kahvila, kahvio. This kind of example is maybe more realistic. What is the difference of kahvila and kahvio? How similar are they? Now, without knowing the language, we can somehow measure. But now, one has 7 characters, other has 6 characters. Aha, so we can't just calculate the difference. And then what about if we have some prefix that is missing? Or again, kahvi, kahvila. Yeah, it is start at the beginning, it's nice alignment, kahvi, kahvila. Perfect match, but then 2 are missing. But in general, let's suppose that in the beginning something is maybe the apple start a new kahvila, they call it iKahvila. And you start to make nice matching, so everything is mismatched. So you have to kind of find this alignment also. And there might be letters missing in between. So what to do? So there are different measures to measure the similarity of text. Basically, character level similarity measures. But then our text is not just the words or keywords, they may be key phrases or titles or just entire documents. So we have a little bit bigger entity. So the tokens are to the next level. So let's suppose we want to have 2 strings and we want to measure their similarity. So then it's not enough just to measure the different words. We don't even know which words we match to which words. I think I will see the examples here, but yeah, let's see. Okay, so this similarity of the words or phrases. So 2 strings are coming as input. So the first step, what is happening is segmentation. Segmentation into words or somehow called tokens. Okay, tokens or qgrams, the different strategies. Tokens pretty much try to find the words. Usually separated by space, but they can be also comma, semicolon, dash, or whatever. If you consider web page and look the title what's there, it can be any content. But yeah, there are the words that can be found there. So then the one string can, so after segmentation, we have the words or tokens what we extract. This can have 3 and this can have 2. One could be isomy. Another one could be isomy kauppakeskus. So it's a shopping mall in the center. 2 words, one has 2 titles, one has 3 words, 1 2 words. 2 is actually exact match, but actually if you consider all the letters, this is a big mismatch. So we should really find out that give more emphasis the tokens and not about the characters. So after segmentation, we do matching, and then what if you put the kauppakeskus isomy or isomy kauppakeskus? Which order you put the words? Aha. So what you compare to what, so you actually have to do matching, find out what words are matching. And then once you have the pairs, that this has to be matched to that one, then you compare at character level. And finally, you sum it up, the different similarities, and get the result similarity score from 0 to 1. Okay, this is a kind of general framework, and if you think, okay, where did I invent this? Did it come from here or somewhere? This is actually nowhere. It's ongoing research what we, Naisla and Radu are doing. So you can't find it anywhere except here. So let's hope this next slide has something. I will put the update slide later. I think I did improve this at least a little bit, but okay. It string is a sequence of characters. Yeah. Okay, now we have the tokens, and let's suppose we have now 2 tokens we want to match at the character level. Okay, first we think of how people do it. So surprisingly many methods, they do it just the binary result. Either it's a match or it's a mismatch. So machine learning, it's a match. Machine learning, mismatch, 0, 1, right? Quite rough. But this kind of, when they divide the words into tokens, compare the words, they just compare, this is the match. So too simple. So that's one mistake many of the methods do. But if we go then the other characteristical measures, transformation based, one actually very commonly known method, edit distance. Has anybody heard about it? Yeah. Half or even more plus heard about it. So this is actually well known. And this is kind of the basic. If you don't know anything else, you probably know this and can implement it. So it's calculates just the number of edits, operations, how much we can need to do to transfer one sequence to another one. So let's consider this machine learning.
Right, you have example.
I have. Okay. The next slide. Okay. Kitten sitting. I don't know what is kitten, but it has some similarities to sitting. So let's see. Output is here 3. So it means 3 operations. So let's see. First, replace K by S. Okay, we have sit. Oh, it's missing. Kitten sitting, so it becomes sitten, then replace I, replace E by I, so then it becomes sitting, and add insert G, we have a G sitting. Okay, so that's the principle is like that. How to calculate exactly, because this is now the optimal, this is the shortest path from how to transfer from here to here. It's also called warping. Warping from this one to that one is it, and you actually need to solve shortest path problem. And basically you need to find out all possible transformation from one word to other one. Put the code letters and make a complete matrix of these two words, and then you start to calculate, fill in the table, possible how the goes if I start here, if I move here, if I move here, if I move here, and you add these numbers. If I go here, it means that I delete something from here. If I move here, it means I delete something from here. If I move diagonally, if they are the same letters, it's 0 cost. If they are different, I have to substitute. So its cost is 1. So I kind of accumulate this cost, and then I fill in the matrix, and then I find out what is the shortest path to find out this other corner. So yeah, I don't go to the details. So if you don't know this by now, you really have to look at it from the internet. So it is solved by dynamic programming, so this technique. And here I just interested the result. So the algorithm to solve it uses this kind of matrix and solve it by dynamic programming technique. Okay, but there are also other way to do it. It's not only one. I don't know how the others will be better, but we will find out sooner or later. So now let's consider here 3 different strings. So A, B, A, B, C, B, A, B, C, A, B, C, D, A. Okay, edit distance, I don't know, here we have, if I delete A at A, so edit distance would be 2. So then I get the second by 2, going to the third, AB, I have to replace this by A and this by C. Okay, I think it's also 2. And what else? From here to here. So I delete B and here B. So I did 2. So this is well. The other alternative is called longest common substring. So it doesn't just how much edit, because if we have completely like, let's take every other letter from one word and the other one, fill in some habits in the between. So then you have to really, yeah, okay, if you take one word like A, and then you take A, B, A, X, A, are they similar? Edit distance is 2, because there are 2 different letters operating with those. But then again, there is not really what is the longest common subsequence that they have? Length is 1. Only one K is common. So here we at least have ABC in all of these 3. So they have something that length 3, that is they really share. They don't say anything except this A. So in that sense, edit distance might be too naive for this kind of example, but here it's yeah. So the longest common subsequence, also how to measure it, I don't know, but I suppose it was the same kind of dynamic programming technique to simple to find it out. Or just brute force, find out all possible substrings and yeah. Okay. So now these are the possible techniques at the character level. Then when we go to the higher level, we want to now segment the words and find out the tokens. So before people use the tokens, they have this kind of compromise solution, or the next step was kind of use not the entire words, but use a sequence of characters, like BI. Okay, let's consider BI. If I have here big moths, and then I have a bicycle, okay, it's more evident that they are similar because they have the same double is repeating in both words. If I have a penguin, the NG and NG are similar, so I have more evidence. Yeah, it's quite low-level evidence, but it's anyway evidence. So now this Q-gram tries to measure how much this kind of low-level evidences there are that they share with each other. So what it does, it segments the string by length 2 substrings. So first and then it calls, okay, we found by. Then we segment here, we find in. Then we find ng. Then we find go, and then we find on. 5 2 grams are found. They are stored. And then we have the other word, we do the same on the other string, and then we try to match these 3 grams. So after that it becomes matching problem. And of course, this Q-gram in general is just now here Q is 2. You could actually have Q equals 3 grams, 4 grams, whatever. So you can extend it. So okay, but then if we start to go this kind of a higher level, why not just do the entire tokenization, so entire words, use the separators. So this is kind of, probably this was invented in applications where we don't consider entire phrases, we just have some database entry, could be some query or whatever, something that used to be a little bit longer, but we don't consider the consisting of separate words or something, or we just ignore it, it's just, yeah. So then the tokenization really relies then on these separators like space, dot, comma, and others. And just use at the word level. Okay, now you can see one difference also here that with these Q-grams, what we have, this unit of this token is always the same length. This is always 2 lengths, so if we start to compare, it's trivial to compare. Is it the same or not? We don't need to consider any more complicated. Just the binary similarity, are the same or not. That's it. If we have words, we will have word 10. We will have word 10. Have. Go. Well, then we have to use the edit distance or some more sophisticated technique to measure how similar they are. So in that sense, it becomes more complicated, and probably one reason why people use these Q-grams at the first place. It's just so much simpler in that sense. Okay, but anyway, both are possible, and let's see where we go with this. Matching techniques. Now, this is the example, the club at the IVU. I don't know, it's a restaurant?
I think in this, it's area.
Area.
Yeah, so it's a place.
Okay, place somewhere in the Australia.
Yeah, exactly, in Australia.
Okay, that's why I told you. 2 sections are from yours, so I'm not going to pronounce them. Okay. Okay, now our text are te klabate aidu and te aidu. So just to different, somebody could just go to Ivo and somebody use the long name. So how to match similar? Okay, this should be this. They are the same. You can see that they are the same entry, but how the computer does know it. Okay, so now we can consider this as a sequence or as a set. If we consider at the sequence, so what we are doing is we are using this kind of edit distance or some other character level method generalized to word level. And then we want to find out how many edit operations we need to transfer from here to here. So what you can see here, one delete, another delete, another delete, and then we have a match. So yes, and after that I think, well, I don't know how it comes to 0.37, but basically 3 out of 5 operations, well, 3 operations, if we normalize by the length somehow, yeah. So how exactly these numbers, but we have a situations can be a little bit more complicated, but the idea can be as simple as that. And then there can be this English guy, so coming here and say I will. So he may have this formulation and then he may even write I will. And then everybody finishes understand, I know what he means, I will. So yeah, it's the same, but then the computer doesn't know. And then it's definitely mismatch here, mismatch. But if you somehow can also measure this, how much it, this could come from here. So this number is not necessarily 0 or 1, is it mismatch or mismatch, it's just number, how similar they are. So you can have this similarity actually 2 levels, at the character level for everything what you match, and then at the sequence of this token level, how we compare the tokens. So how we compare the characters of 2 strings and how we compare the tokens of 2 phrases. The other approach set. So now the sequence doesn't matter. We just take the words as they are. Take what at the I. And what we do, we match. So in this example, it seems more like pairing. So yeah, we find out that they are matched and they are matched. Okay, and then we see, okay, how we calculate. Okay, but there are several alternatives. One is matching coefficient, MC. It says that, yeah, 2 match out of, what is the maximum? Maximum, this is length 2, this has 5 tokens, so it takes the maximum. 2 match out of the 5, 0.4. Overlap calculates number of matches divided by the shorter one. Shorter one is 2, perfect match. It doesn't care about the extra words at all. Jacquard, I think this is my favorite, it's the most sensible, I don't know if it's the best one, but oh, okay, looks like yes, the third has been, one of them has been removed completely. So it calculates the intersection divided by the union. Size of the intersection, size of the union. So intersection is 2, and then if we take union of all the words, then we see I will club at 4 unique words, right? So 2 out of 4, 0.5. And dice is, this I don't remember what is the rule of dice. Maybe it's just the sum of this length. So this is, yeah, okay, in this case this is removed, so this is a little bit question mark, should it removed or not, but I think if this is 4, this is 2, so the sum of them is 6, so yeah. So different techniques. And even this kind of back of tokens. This back of tokens is used document clustering quite a lot, so that's why we're to mention. So now the idea is that we consider the 2 sequences, put them together as a big back, and then we find out what are the unique words there, and then we collect all the unique words, and we call it back, here the back of tokens. So we have the 4 unique words, T club at Ivy, and then the original string is represented by a frequency vector. How many times these words are appearing at this phrase? Here we can see that the is appearing twice, club once, at once, Ivy once, and here T is once, Ivy once, others 0. Okay, so we have frequency vectors, and then we use numeric comparison. Aha, we transfer the data actually to the numeric feature space and compare. But yeah, Jutland for Manhattan distance, we have different distances. But then again, if we have short titles, short phrases, there are mostly ones and zeros, so this is not so clever in my view. But in the document where you are repeating the same words many times, then it actually will work out. So, but yeah, so many different ways to do this similarities. So token similarity, exact matching with just 0 or 1, or approximate matching, use some character level measures like edit distance. Okay, so here are some example. This is quite old already. Monge Elkan presented 96 this kind of method. Yeah. Okay, let's see. The gray color. So this is the one letter, gray color is the other one. And you can see the difference here. British English, American English. So yeah, harmless. You can expect this kind of difference happen. And also here, British English, American English. So the differences are there. Semantic, perfect match. Syntactic, there are two differences. Oh yeah, and forget the verb. There's an article and the other one didn't have article. So how to do? So hair gray color. So we calculate here similarity first between all possible words. Gray and hair, very low similarity. Gray and gray, very high similarity. Only one letter change. Color and gray, very low. Color very low. Color gray, low. Color high. Okay, what this measure does, it takes the maximum of each of them and then it sums it up the maximum similarity. So it's kind of a 3D match. So gray is matches, whatever is the maximum function. So gray matches to gray, so we take that one. Color matches to the color, and we take that one. So these numbers are summed up, and then the result, what we have, take the average divided by 2. So average similarity is 0.85. Yeah. So now we are matching from here to here. Maybe we should also match here to here and take the maximum, minimum, average or something. So many choices. And I don't have answer what should we use. We are, like I said, it's research and progress. Answers are coming. Truth is somewhere out there. We just haven't found it yet. Okay, let's see. These are a couple of examples. These are now simple measures. This is edit distance, some Q-gram measures, and we have some cosine distance. Okay, this seems to be not coming from the previous example, but anyway. So now, example from Joensuu. This student did one thing right. Pizza Express Cafe, Pizza Express. Has anybody know where's a Pizza Express? Best kebab in the town. Free advert. They don't give me any cheaper for saying it. Yes. That doesn't still mean much because there's not so excellent kebabs places around, but that's still the best. But yeah, Pizza Express Cafe, Pizza Express. So we know it's the same place definitely. So they should be high similarity, but because of the cafe here, it really always is down, so it's 80, 70, 80 something. Then we have lounasravintola Hinja-ravintoloita. Okay, what on earth is that? Here's the name of the service, lunch place Hinja. KY is like, I don't know, it's not limited. It's not Osakeyhtiö Oy. It's not company, it's this kind of a community, private something, not commercial, non-commercial enterprise. I don't know what on earth is that, but anyway. So it's kind of an abbreviation like limited, I don't know, the unlimited or English whatever. And ravintoloita, restaurants. Why it has this word? Because it came to some service directory. We use Google search and we find out service directory, it was one entry there. This Lounasravintola Hinja, and they have with this, they put the title like that. people want to put extra information in the title so that search engine would show it higher for whatever reason. So that's what happens. And this is a title from their own webpage or whatever other sources. And now the similarity, it should be higher because they are the same, but now because of this extra words, it's put this lower. Yeah, so this is a tricky. Our next one is Kioski Piirakkapaja and Kioski Markkakahvio. Two good places to eat Karelian pie in the city center, in the marketplace, especially summertime. Of course, you can be hardcore guy and do it on the winter time, January -20. I don't know if they even open, but they are different. Two shops neighboring each other. Names are just similar. Well, okay, actually it's only the kiosk that is similar, so, but yeah, anyway, so. Kauppakulta Keidas, Kauppakulta Naula. A lot of similarity, but again they are different. And now you can think, okay, why I can conclude they are different? Okay, one reason, of course, they are in Joensuu. I know places in Joensuu. But I could conclude it also otherwise. Kulta Keidas, Kulta Naula. This is the name of the place. This is the name of the place. This kauppa is just a shop. So this is a general word, and this is the erisnimi. What is erisnimi in English? This is a specific word. This is a general word and this is specific. So this should be given more emphasis. And therefore we can see that they still share something, the kulta, gold. Gold oasis, gold bear. So 50-50 there, but this definitely should be lower, yeah, okay, whatever. And then Ravintola Bierstop Pub, Baari Bierstop R-Kylä. Here is an abbreviation of Rantakylä. You want to compress same information. It's not important Rantakylä. Actually, it may be infamous that it's Rantakylä. Just come anyway. So, yeah, so they are this, but yeah. Ravintola Boxes, Bar Boxi, Karsikko also again this the place, but otherwise they really it's Boxi. Boxi is just you don't find many places in Joensuu named Boxi. So if you have the same, it's most likely the same. So this should actually be higher. Play Baari, Ravintola Bar Play, Ravintola that's again. So you can see this is what the simple measures do, and I don't think the better measures can really get much better. So this is so much context dependent already that. You can think of how would you solve this problem if you want that they should give lower score and the others should give higher score. How would you solve it? So those were my ideas that how I might try to do it. But yeah. Okay, that was about my part. So unfortunately I used the wrong slides. I will update it. There will be a little bit more information and examples the other slide, but not that much. So that means that